Hello, fellow gamers. Welcome back to part 3. It's past midnight where I am, so I'm trying to just get this done. I don't know if you can see it because of my side camera. Shout out to side camera. Good guy. Part 3. Implement a flash calculation function to calculate the vapor and liquid compositions of a flash drum given a feed comprising of 10 moles each of methanol, ethanol, and water at a temperature midway between the dew and bubble temperatures and a pressure of this amount. So, what is this asking me to do? I need to make a flash calculation function and calculate the vapor and liquid compositions of a flash drum with some known composition and a known temperature and pressure. So sweet, let's go ahead and take a look at a picture I drew about this. So we're going to have some feed, and then the compositions of the feed can be represented by Z. And that feed, I think, usually it comes in as a liquid, right? And then you decrease the pressure, and that allows some of it to vaporize. But essentially, it's like a saturated liquid, and then you let some of it vaporize. My phone is right here. There's nothing on it, but I'll go ahead and put it down here just so it doesn't distract me, because it probably will. Although it's past midnight, so I'm probably not going to be getting any texts. There's a "you up" joke to be made somewhere, but I won't make it. I kind of did, though. But anyway, so it's going to flash into a vapor portion and then a liquid portion. And then you take the liquid and vapor portion out. That's kind of how, a flash tank works. It can be a continuous process. There are, like, batch flash tanks. You could do it as a batch process, too. We're going to kind of imagine it as a batch thing right here. But we have a feed come in, and it's separated into a vapor with a vapor composition and a liquid phase with a liquid composition. And this is, of course, going to be governed by Raoult's law. So we know that the Yi in the vapor phase times the pressure of the flash tank is just going to equal the composition of the liquid phase times the gamma that I calculated before times the saturated vapor pressure. So with that in mind, I think we're ready to go ahead and start taking a look at the actual homework, or at the actual coding. So I went ahead and copied down some of this from before, but also wrote in a couple things. So the number of moles in each of the feeds is going to be 10, 10, and 10. That's what it asked for before. I went ahead and wrote out a Z. I don't think I'll end up using it, but I wrote it out. The molar composition is just 1/3 each. It's equimolar. The flash pressure is going to be this 101,325, and then I kind of cheated a little bit. I maybe should have written this on camera, but I did it off camera. So the flash tank temperature is the mean. It needs to be at midway between the dew and bubble temperatures. So to do that precisely, I took the average of the NRTL dew temperature and the NRTL bubble temperature at the specified pressure. So that's what this is doing right here. And of course, this 0 is in there because I want to look at just the temperature term, not the composition term. And then I went ahead and wrote in this gamma and this pvap just as notes, things I can kind of copy down later. So let me go ahead and restart the runtime, restart and run all. I meant to do this before I started recording, but that's fine. I think we'll be okay anyway. And let's see what happens. Take a look in this book. Figure this out. Should hopefully run without any errors, and it does. Sweet. So I'm on my 20th cell down here. That is tough. But anyway, where was I? So we know all this stuff, and I want to implement a flash calculation function. So I'm going to start out by actually writing a vapor-liquid equilibrium function, and then we can take the root of this vapor equilibrium function in order to solve for the flash tank's conditions. But first off, I'm going to talk about this EXPit. This is a SciPy optimized function. Well, actually, I don't know what library it's in. It's a SciPy special, I think. And so you look at it, and what this does is, the math is actually shown right here. Yeah, the EXPit of the variable x is just 1 over 1 plus e to the negative x. And what that does is that allows you to transform a variable x that could be anything into a variable that is no matter what in between 0 and 1. So this works out really well in a lot of cases, as long as you're not getting super, super close to 1 or super, super close to 0. It won't work exactly at any of those points, but it will work. It can take in inputs from -6 to +6. It basically means you don't have to actually bound your function when you put it through the root solver, which is great because that reduces the work we have to do. So we're going to be working with this all in the EXPit domain. And I'll flush out what that means a little bit more as I'm coding it. But this is a really great chart to help you understand what EXPit is. I think this pretty, it's saying you give it an X, and the EXPit domain is somewhere between 0 and 1. So, sweet. But we'll go ahead and give this V. This V is in the EXPit domain. And then I need to, of course, define the function. So define vapor-liquid equilibrium. And then what do I want to do? Well, what I want to return is this, this equation over here, but probably like one side minus the other, so that it's all equal to 0, right? So I could go ahead and type that out, and might as well go ahead and type it out. So it'll just be x times the gamma times the vapor pressure, and then minus the gas phase mole fraction times the pressure. And I'll go ahead and maybe copy these two down in there. Sweet. So we need to somehow get this x and this y in order to sort of solve for this vapor equilibrium function that we can then take the root of. And so how can I go, well, actually, no, I don't need to solve for the P because I already know the pressure. It's this flash pressure. And I do already know the temperature, so that allows me to calculate gamma and the vapor pressure. Although, actually, I can't calculate gamma yet because gamma needs to know x. So, yeah, how can I go about doing this? Well, let's think about what this vapor-liquid equilibrium actually is, right? I know that you're going to get some composition, y, coming out the top, and then some composition, x, coming out the bottom. So I can actually go through, and maybe I can start out by saying that the number of moles coming out of the vapor phase is just going to be this EXPit of V, right? So V is sort of like our, and V is our guess, or no, V is going to be the actual, it's going to be like the composition of the vapor phase, we'll call it. Yeah, I think we'll start out with we'll do the vapor phase. So the number of moles in the vapor phase is just going to be the number of moles in the feed times the fraction that goes into the vapor phase. And then likewise, the number of moles going to liquid phase is just going to be the number of moles in the feed minus the number of moles in the vapor phase. So sweet, I ran that, I didn't mean to. Because I still need to somehow flush out what are x and y. Well, you can find x is just going to be the number of moles in the vapor phase divided by the sum of all of the components in the vapor phase. So if there's 5 moles of water, 5 moles of ethanol, and 7 moles of methanol, then that would be like 5, and 7 divided by the sum of all three of those components, 17. And then likewise, y is, I'll just program y the same way. Y is going to be the same thing but for the liquid phase. So yeah, and did I do that correctly? No, I did it in reverse, because why would I do it correctly? This is actually something that, when I was practicing this, I screwed up, and it took me like half an hour to figure out what I was doing wrong. It was pissing me off so bad, but I did figure it out eventually. So this is awesome. We now have this x and y defined, which allows me to define gamma, because then I know the liquid phase mole fraction, and then I can know the vapor pressure, and that'll let me solve for this vapor equilibrium, vapor-liquid equilibrium thing, which the root of the VLE should be the values of V that are the actual vapor phase composition of the final thing. So if I go ahead and maybe run root of VLE, and then I'll give it, I need to give it guess for the initial conditions, we'll just say that our initial guess is 3 zeros. Well, I'll say np.zeros, and then I'll say 3. And the reason why I'm guessing that it's zeros is because this VLE, this EXPit, when you have an array like this being EXPited, if they're all the same, if all the values of EXPit are 0, that means that it's equimolar. That would be the same thing as saying something is equimolar. And the cool thing, the reason why I guess that is because that guess is not really going to be right. It's certainly not going to be right in this situation, but at least it's kind of like approximately, maybe kind of like what you would see, because you're going to expect to see some of the component in the liquid phase and some of the component in the vapor phase. So that's like a good initial guess. It can get to the final answer using that initial guess most of the time. So it has a problem. Y is not defined. Maybe because I haven't ran that yet? Yes, okay. So I got 3 answers. I got this array of 3 values. This is in the EXPit domain, so I can't just look at it and tell if it's right or wrong, but it looks like 3 answers. So let me go ahead and maybe work this into a larger function. So I will define a new function, define the flash tank, flash temperature and pressure, and that will be defined as, what will it be defined as? Well, or what will it be defined as? What will we need to pass into this function? Well, we can give it the number of moles of everything in the feed, so the moles of each component in the feed, and then we need to give it some pressure and then some temperature, which would just be this P flash and this T flash. And I'll go ahead and say that, and I can come down here and lodge that function in the other function. And so now, once I've done this, I need to run the root function, right? So I'll take the root of VLE, and my initial guesses being a bunch of zeros. And then what do I need to do? Well, I'm going to break it up with some spaces real quick. I want to return, well, let's see, what do I want to return? It says that I need to find the vapor and liquid compositions of a flash drum given a feed. So I want to find the vapor and liquid compositions. I guess that just means I need to return a value of X for the vapor and then Y for the liquid. Did I do that right? No, I did it out of order because I don't know. I seem to have forgotten how to do it. And then on top of that, let me maybe return, I don't know. We'll call this the vaping. Don't do it. Vaping's bad. Vaping's bad. The vape frac. I'll call that the vapor fraction. And so that's basically saying of the feed, what amount of the feed goes into the vapor phase. So sweet. I have this root. What can I do with this root? Well, I can go ahead and say that the vapor fraction is actually going to be the EXPit of this root function. Actually, that's a good thing to check outside of the loop is what is the EXPit of that? Oh, it's because I need to put an X on here. I need to just look at the X, not the whole thing. Yeah. Okay, so this is saying that the vapor fraction, it's saying that, I think this is methanol, ethanol, and water. So it's saying for the system, 28% of the methanol goes into, goes into the solution, or goes into the vapor phase. 28% of the water and 27% of the water, 28% of the methanol. But that's only when you, that's only with those initial guesses, that's with some of these other terms being assumed from outside the function. So that shouldn't be the final answer, I don't think. But anyway, continuing on, I know that these are the vapor fractions, right, of each component. So I can say that the number of moles in the vapor phase is just going to be yeah, it's just going to be this vapor fraction times the number of moles in the feed, and then the number of moles in the liquid phase is just going to be, let's see, the number of moles in the liquid phase is just going to be the number of, so the number of moles in the feed minus the number of moles in the vapor phase. So sweet. That solves the NV and the NL. Now we got to go through and calculate X and Y. So I can go ahead and just copy this, I believe, right? And say that I'm going to copy that. Get rid of, tab this over so it's at the right level. And now I've defined X, I've defined Y, I've defined the vapor fraction. Let's go ahead and maybe run this function. So it ran okay, it didn't give me any errors upon running the function. So now let me go ahead and run a flash temperature pressure calculation. NF is just this variable from up here. P, I need to specify as the P flash. So I'll just say that that is the P flash, and then T is going to be equal to the T flash, right? Nope. PFOS, T flash, P flash, P flash. Sweet. Little inside joke, I guess. So when I run this, I get an error, because of course I do. Unifac didn't like, EXPit didn't like what I passed into it, probably because I didn't do the .x. I just want to look at the solution to this, not any of the other things that this solver in root is going to return to me. So that should fix that issue. Let's see what happens. Okay, so I get 3 values. Let's see, what do these values say? Well, so this first one is saying that I got, okay. Yeah, so this is saying that in the liquid phase, the Y, no, in the vapor phase, the Y, in the vapor phase, the fraction of methanol is this, the fraction of ethanol is this, and the fraction of water is that. And then, sorry, I just gotta check this out. And then there's something, likewise for down here. And then it's saying that, well, let me go ahead and return this last one instead of just as the vapor fraction times the number of moles in the feed, which is actually going to be, I'll actually return the sum of that. So that's actually going to be the number of moles in the feed that, the number of moles in the vapor phase, right? So this should work, right? Yeah, sweet. So it's basically saying that of the 30 moles we started out with, 19 go into the vapor phase. And then the vapor phase's composition is this Y right here, so that would be all those numbers, and the liquid phase's composition is all those numbers. And yeah, sweet. So is that answering the question the way I wanted it answered? Calculate the vapor and liquid compositions. Yeah, that's the way I understand it. So, sweet. Let me maybe go and let's make a quick comparison to something else. So I have some notes over here. This is what my professor did in class. Let me see if I can zoom in on this. So it looks like the compositions are the same. He's just got them in a different order. So go ahead and maybe copy that and come down here. Can I paste that? Yeah, so okay. Yeah, these two arrays are the same. If I were to go and say take this number, this final number, and then that's just going to be a bunch of errors. If I go ahead and multiply that by 30 moles, I will get 19.25, and yeah, sweet. So he got the same answer as me. This is based on the professor's function that he did in class. So sweet. With that, I've shown the I've shown that the final composition of the flash tank at the specified temperature and pressure is going to be this in the gas phase, this in the liquid phase, and overall of the 30 moles, 19 moles of material are going to go into the gas phase. And it appears as if you don't really get a great separation here. You get a good amount of water, I guess, in the liquid phase, which makes sense because it has the highest boiling point of all three of the components. But yeah, with that, I have implemented a flash calculation to calculate the vapor and liquid compositions of the flash drum given a feed comprising of 10 moles each of methanol, ethanol, and water at a temperature midway between the dew and bubble temperatures at a pressure of 101.325 pascals. And that finishes up my homework 4. So thank you very much for watching this video. I hope you learned something, and I hope you got a lot out of it. And yeah, hopefully I'll see you again someday. Thank you very much for watching, and I hope you have a nice one. Bye-bye.